All right, so let's talk about support vector machines. These are very simple machine learning models that just draw a straight line boundary between two categories, but it can be in high dimensions, and this turns out to be extremely useful, far more than you might imagine. So I go to Colab. First, we're just going to make a data set just to work on that is just going to consist of some random colored dots that we're trying to differentiate. So I'll put that code in here. All right, and so it's going to have two Gaussian clusters centered at these coordinates, -1.1 and -2, and 1.5, 1.6. And then it's going to create random Gaussian dots, or Gaussian distributed dots. Although, since we're defining the seed for the random number generator, everybody will have exactly the same pseudo-random numbers. And I think it'll draw a chart when it gets them. Which, there it is. So there's red dots and blue dots. And as you can see, they're separated by enough that there's in fact no overlap. So if I wanted to have a machine to automatically discriminate between these, there's a problem here. I could draw a line like this, and I could draw many lines. I could draw a steeper line. I could draw a shallower line, and any of those lines would 100% separate the blue dots from the red dots. There's just a gap between them, and the best decision line between them is not clearly defined. So for support vector machines, the rule is you just choose the line that gives you the widest road, so the widest possible gap between the two categories, and that means the line is in fact completely determined by just two dots, the dots on the outside here. And perhaps one up here. So that's why those are called the support vectors. Each dot is called a vector, and this is called a support vector machine that is in fact defined just by the instances on the edge. All the rest don't matter at all. And that's why I say this is really an extremely simple way to separate categories, and it turns out to be very powerful. So this is going to create a classifier, and it's going to just fit using the default settings for everything, which is going to be a support vector machine. And then we're going to check the accuracy of the classifier. And of course, it should be 100% accurate with this data because there is no overlap between the dots. So let's see how this looks. All right. And there it is. So it draws a border between them with the decision boundary, as you can see. And the accuracy is 100%, as you'd expect. And here's some of the weights used by it, which is basically going to be the slope and intercept of that line or something like that. All right. The weights of the x and y features are similar. So because the x and y features are both equally useful to discriminate between these two. All right. Now, this you get to see some of the consequences, some limitations. If I multiply the y-axis by 100, to just magnify it here, so I create another thing where I make tr expanded x is 100 times the previous tr expanded x, and x is the two coordinates, x and y, so I use the element numbered 1, not the element numbered 0, which is the y-axis. So this will create another array, or list, or whatever it's called in Python, the list of items trx, and another one called expanded, which is going to have one axis multiplied by 100. So when you plot it, it looks just the same, but the scale is different. This is 100s here and 1s here. And now, when we train the model, we're going to get different results. All right. You see the line is very horizontal, but I think the actual shape of it is very much the same. A blue dot here and a blue dot there. And up here, it was, well, that one's not good. I think it did not choose exactly the same line, I think. it got much closer to this because the problem is here, it considered it acceptable to be very far from that blue dot, but now that I've multiplied the vertical distance by 100, it's weighting this error much more than horizontal errors. So it's strongly inclined to choose a much more horizontal line here. And that's, again, pointing out what I said last time, that in machine learning, you need to normalize the data first. If they're of a different scale, then you will have weird distortions like this, where it's very, very unhappy about any vertical distance, which it counts as 100 times more important than the horizontal distance. All right. Anyway, so there's more things you can do here to change the scale and play with that. And now we can move on to data that overlaps. So in this case, you can't use the simple support vector machine algorithm I described, where you draw a line and then choose the widest possible width of the road, because there is no line that will reach 100% accuracy. So you have to use a different version of support vector machines where you allow some violations, and then you try to minimize the violations. So here, I think we left the centers the same, and I just made the standard deviation bigger, which is a way to make them overlap. So there they are. Now the red is up here and the blue is down there, but there's some overlap. And now when we train it, there's a normalization factor, C, which is a meta parameter that controls how much overlap you're going to allow, how many violations you're going to allow near the border. And so we are going to try various values of C here. So there's the fit with C of 0.1, and C of 1 is very similar. And there should be more coming. Perhaps it's still running. Here we go. All right. So with the C very small, it totally fails. The blue means it's categorizing everything as blue. And here it is as this normalization parameter increases. Now the line is getting closer. Now I hit a reasonable value of the regularization parameter, and it does a reasonable job sorting it out. Let's see if I can get this to scroll to show more on the screen there. And here's another. And here's another. So this is what you do. You just vary the parameter until you find a region that gets you a good fit. And in the lecture that goes with this, we'll talk more details about what this C is, but the C is what allows some degree of violation of the separation. And I think I did not describe C in this project, but it's described in the chapter. All right. And again, there are some flags to find there. And now let me shrink my font a little so this gets easier. All right. Now let's try a data set that curves. So you can't separate it with just a line. And this is another standard model, and there's this thing called make moons just for this purpose, to make these curved separations. So now we have blue dots up here and green dots down there, and we want to separate them. So we can train a model here. And what this does is it adds polynomial features. And this is something we talked about in a previous lecture. You're clearly not able to draw a line through this and get through. But what we're going to add is polynomial features. So it's going to add higher order values like x squared and x cubed on the x and y axis. So you will have more dimensions and higher dimensions. And in those higher dimensional spaces, a straight line will appear to be curved on this graph. This is a way to use the math that only fits straight lines and scale the features so in one of those other plots it will be a straight line. So let's give it a try. And so this shows it's going to be polynomial features, then it's going to scale them so we don't have that problem of having one axis bigger than another, and then it's going to do a linear fit. And so this will show the decision boundary of the support vector machine on the model, including some polynomial features. And now you see it does a good job. It draws this curve through it, and this curve is basically a third order polynomial, which means it's got some linear component times x cubed plus something times x squared plus something times x plus 1, and that is a straight line in a multidimensional space where one of the axes is x cubed and one is x squared and one is x and one is 1. So that's why the fitting of straight lines is far more powerful than you might think it would be. And there's a thing called polynomial kernels, which are talked about in the book, and they are a mathematical trick to do the same thing but make it much faster than having to recalculate those polynomial features and add them to the data set. So this is what implements that, the polynomial kernel. And you see it ends up with essentially the same results, but it is faster to calculate. All right, and here you can even go up to a 10th degree polynomial if you like, and then it's able to be even curvier, and probably it's going to not really, this is going to probably be an example of overfitting, where it's more accurate on the training data, but it wouldn't be as accurate on test data, which we haven't added here, additional points that obey the same pattern, same trend, but have different noise. But anyway, you can play with it and see how it goes. And those are support vector machines. So I'm going to stop this recording.